Okay, so what I'm trying to do with these first couple of classes is kind of go through the conceptual concepts. Cannot talk tonight. Concepts needed to understand how we produce the material that comes out of a volcano. How do we actually get a volcano? Because on Earth, it's hard to get a volcano. We don't have them everywhere. They're only in certain areas. And like I said, we know where this stuff comes from, but it comes from a place where we haven't been directly. So that complicates our understanding of how do we actually produce magma, what are we producing it from, and how do we get it to the surface. But as I said just a few minutes ago, hey, we have pieces of this stuff. We have ophiolites that break off the ocean crust and luckily get transported up here where we can study them, see them. So we can look at the base of the ophiolites and see what we think is probably melting to produce a lot of the magmas that we have here on Earth. And as we talked about last class, we also get these xenoliths, these hitchhikers that come up in the magma. They get plucked off the magma chamber and conduit walls. This is a great shot here of lots of xenoliths that came up in some basaltic magma that was erupted in China. So we can take a look and say, wow, there's pieces of the stuff that probably melted to produce the material that's encasing it. And when we look at it, we see lots of olivine, 50% or more, lots of pyroxene, and a little bit of garnet. We know the depths from which this material comes from. We're able to look at earthquakes of ascending magma. And we now know the rocks that are there, so we have an idea of the temperature and pressures where these sorts of rocks are stable. So here's a shot of another variety of peridotite. This one's a little more garnet heavy, as you can see. But we know this is dominant in the upper mantle above 400 kilometers in depth. Olivine rich, pyroxene rich, garnet rich. So these three primary phases. Now, if you completely melted this stuff and let it crystallize down deep, you get the same stuff. But we can look at these ophiolite sequences and see that the melt that comes off it is not the exact same material as what we melt. Gabbros are different than peridotite. So what we think is happening is we're not completely melting the peridotite, we're only partially melting it. Maybe 5 to 10 to 15%. We're going to look at some phase diagrams here in a minute. We'll start on them this week and then we'll really get into them next week. And we can see that with these phase diagrams, when you first start melting material, you get something very different than the material itself. And we know that the very first melt that comes off is really rich in iron, magnesium, and silica. And those are the three primary constituents that we find in basaltic magmas. So if you take a peridotite and you only melt 5 to 15% of it, you end up with basalt. And we'll look at phase diagrams here in a bit to try to explain how that actually happens. So if the iron, magnesium, and silica preferentially comes off in the early stages of melting, that means that the peridotite that gets left behind gets depleted in that stuff. You basically drain that away, and the remaining stuff has less of it after you produce a little bit of partial melt from it. And you can see this in those ophiolite sequences as well. Now, unfortunately, when we look at mantle xenoliths, stuff that comes up in the basalt, it's coming up from the area that's melting. So it's been depleted in the materials that became the melt. And when we look at ophiolite sequences, the peridotite that's attached to that ophiolite sequence was probably the source of the gabbro and the sheeted dikes and the pillow basalts that are above it. All that stuff is basaltic melt. So to find some peridotite that hasn't been depleted is pretty rare. So in order to really do experiments on this, we artificially create what we think the original stuff was, because we don't have much of the original stuff, because all the stuff we have has been partially melted. That's the only environments that we tend to get them from are volcanic environments where they've already gone through this partial melting stage. Okay, for those of you that have had this before, you're probably hating to see these terms right now. Liquidus and solidus. You guys remember anything about the liquidus and solidus?
Solidus is when it is the line on a phase diagram at a specific given temperature or pressure that means it's transferring from one state into a solid, or like it's switching from solid to liquid essentially, I think.
Yeah, you're pretty close on that. That's where everything gets melted, okay? Let's take a look. So, one way to think about it is the solidus is going to be the line on our phase diagram, temperature versus pressure. You can think of it as temperature below which everything is solid, okay? It sort of marks that transition between it's totally solid and now it's going to start melting, okay? When you hit the liquidus, it's the temperature above which everything gets melted. And you're going to see on these diagrams there's going to be a separation between the liquid and solidus. And then this is going to be the area where things are melting partially. They're not completely melted, they're not completely solid, they're in between. And remember, magmas are mixtures of many minerals. We're not just melting olivine, we're just not melting pyroxene, we're not just melting garnet, we're melting all three. And when you have mixtures of elements, the melting can be kind of complicated.
I'm pretty sure that window's open.
It is.
Now that I've been sitting here.
It is. Keeping that COVID.
Does it close?
It does. You can close it if you're cold. Okay, so I asked this question last class. Why don't we have volcanoes everywhere? We only have them in certain places. Well, we don't have them everywhere because it's not hot enough to melt them everywhere. In fact, most places on Earth, it never gets hot enough to melt magma. But as you go down in the Earth, it gets hotter, right? At the surface of the Earth, olivine melts somewhere around 1,400 degrees. Okay, you can go down deep enough where it's going to be 1,500 degrees, right? But olivine doesn't melt at 1,400 degrees at those depths. It melts at a much higher temperature because the pressure retards the melting. So you have to add in extra heat to overcome the lack of movement that you get from the pressure. So as the temperature increases towards the melting point with depth, the melting point also increases, unfortunately. Because the more pressure you have, the more difficult it is to break bonds. So even though it's getting hotter, the melting point's getting hotter too. And most places on Earth, the melting point stays ahead of the temperature. So it's getting hotter, but the heat required to melt it is greater as well. And in most places, your heat just never gets to the point where it can break the bonds in the rocks that are in that area. Okay, we're spending the rest of the class talking about how we actually get rock to melt, even though it's really difficult to do so. We have the geothermal gradient. It gets things hot, but not hot enough. We add in some extra heat from radioactivity, and generally it's still not hot enough. So something has to happen, and it needs to be related to plate tectonics because that's where we have our volcanoes. That allows us to get enough heat to not only hit the melting point, but then all the extra heat that's needed to overcome the latent heat of fusion and break all those bonds and get melting. And we know of 3 ways that we can get rocks to melt. The first is to reduce the pressure. Without somehow cooling off the material. So the temperature is going to stay hot. But the pressure has to drop. So this material has to somehow move closer to the surface in order to melt. There's a couple ways that we can do it. One is with plate tectonics. So when you have mid-ocean ridges that pull material basically apart, right? What does that do to the pressure beneath it when you remove the rock on top of it? It lowers the pressure. And you can suddenly change the conditions and allow for melting. Another way to do it, if you have, here's the surface of the Earth, right? You have this material here. It's really hot. It's close to melting. You just can't quite get there. But if you can remove the pressure somehow without changing that temperature, you might have enough heat to melt it. And one way would be to have a landslide off of a volcano that removes a bunch of material above your volcano. So if you get a big landslide off a volcano, it's possible that that could induce melting. Some people have suggested that long-term erosion of a volcano could remove enough material to cause melting. What's going on with our climate right now? We have climate change, it's warming, right? What's happening to ice caps on Earth? No. They're melting. Ice caps provide a fair bit of pressure in polar regions, and one thing that's being bantered about is, will we see more volcanic activity in the polar regions now as the ice caps thin and the pressure drops? I don't think statistically we're seeing that yet, but we may be in the early stages of this ice cap melting thing. Yeah.
So because this might be a little controversial, and I'm no pro about this, but because the ice caps are melting, wouldn't that would increase our ocean levels, correct?
Yeah.
And wouldn't that also cause a pressure change?
That would increase the pressure in the oceans, but we're not talking about a huge, when that water in the cap spreads out over the whole ocean, it's not that much.
Okay.
The pressure drop at the polar regions would be significant. The pressure rise over the rest of the oceans would be pretty small, just because that volume of water is being spread out so much. So somehow if you can drop the pressure above a magma body or a potential magma body, you could induce melting. So that's called decompressional melting. A second way would be, got to make it hotter. We know that geothermal gradient alone doesn't do it. We know radioactivity added in doesn't do it. We need another heat source. This is actually probably a pretty rare way of doing it, though. You would think, oh, you know, if I need to melt something, I just need more heat. And that would work, except it's really hard to do.
Yeah, where are you going to get that?
Where are you going to get extra heat?
So it would be like, are we talking like maybe close to magma chambers?
Yeah, and that's probably what, and this is a crass term, but I've heard petrologists refer to it as a basaltic enema, where you have basalt, which is already melted, right? And it's super hot. And if somehow it moves through a crack into an area, it can release enough heat because it's already exceeded the latent heat and everything else. And as it starts cooling off, what's going to happen to the heat from that basaltic injection? It's going to be released into the environment around it.
Okay.
So not probably enough to cause a lot of melting, but it's one particular method. But like I said, it's probably a pretty rare method.
Okay.
The thing that we think causes most of the melting is probably this last one, especially in subduction zones, is you're changing the melting point of the rock by adding water to it. You're lowering the melting point. So instead of adding more heat or changing the pressure, you're just lowering the temperature at which the stuff will melt by adding water. We know water lowers the melting points of lots of different minerals. And when we look at subduction zones, they actually contain a lot of water. What's being subducted? So the ocean crust is slipping down, right? That ocean crust has been sitting out in the ocean for millions of years. All of the minerals in the ocean crust get hydrated, turn to clay. So it carries down lots of water. At some point, they become hot enough that that water is liberated from those clays, goes into the mantle, lowers the melting point. It's already hot there, and if you lower the melting point, you can suddenly get melting. So that allows the silicate bonds to break and melting to happen. So those are the three mechanisms. We're going to come back to those here in a little bit. So we know we have four factors that influence the amount of melting we can get. One is the rock that we start with. We know pressure and temperature affect the amount of melting. Obviously, temperature does. Hotter the temperatures, the closer you can get to the melting point, and then once you do start melting, the more melting you're going to get. Pressure plays a role. The lower the pressure, the more things tend to melt. But then, as we just mentioned, water. Volatiles can change the melting points of different minerals. It can lower them. So this last one's interesting because you always think about, in order to melt something, I got to change the melting environment. Well, what that is saying is that you're not doing anything to the environment. It's the temperature and pressure that it is. You're going to change the nature of the rock. You're going to make the rock less. You're going to make the rock easier, less stable, easier to melt by lowering the melting point. How many of you guys have seen one of these before? How many have not? Okay, this is a phase diagram for plagioclase. Okay?
It looks different than Ivy's diagram.
This is a solid solution phase diagram. My guess is that you have seen the one I'm going to show next, which is a mixture of two different minerals. So with a solid solution, it's basically a mineral where you can change the percentage of major cations within it. So plagioclase has a sodium-rich end member called albite, and it's got a calcium-rich end member called anorthite. Okay? This shows the difference in melting temperatures based on composition. Okay, so this line right here. Okay, and then we have this line right here. Below this temperature, what do we have? It's all solid, right? Above this temperature, above this line, what do we have? All liquid, okay? Here, what do we have? So if this is all liquid, this is all solid, it's partially melting in this range, okay? It's not completely melted. So here's what happens with these diagrams. Let's start out up here. We're going to start with this composition and this temperature, right in the middle. So that's a 50-50 mixture of the two, right? So if you looked at the structure of the plagioclase, about half the cation sites are going to be taken up with the sodium-rich, basically the sodium cation. The other half of the sites are going to have calcium, okay? So you got this nice mixture. 50% of the cation sites are sodium, 50% are calcium. We start to cool it off, okay? Still liquid, still liquid, still liquid, still liquid. When we hit this point right here, what starts happening? You start getting some crystallizing, right? And what it shows here is that this is the liquidus, okay? It shows the composition of the liquid. This right here is the solidus. It shows the composition of the solid. So when you hit this point right here, you start to form a crystal. What's the composition of the crystal, the solid? It's way over here, okay? That is the composition. It's very calcium rich initially. Because you're taking calcium out preferentially, right? What does that do to the composition of the melt? Makes it less calcium rich, right? So it follows this line. So as it cools off, the liquid follows this line right here. The crystal follows this line right here. By the time you get to here, it's all solidified, right? And what's the composition? 50-50, just like when you started. If that was hard to follow, let's go the other way. Because this is what we're talking about with melting, okay? So let's start down here. It's all solid, right? 50-50 mix. Crystal that has half of its cation sites sodium, half of them calcium. Let's heat it up, all right? What do we have right here? Solid 50-50 mix, right? What happens at this point right here?
Start to get melt.
You start to get melt. What's the composition of the melt?
Very sodic.
Follow it over to the liquidus. This is the first melt. It's almost all sodium, isn't it? What if we only melted 1% or 2%? We only go up a little bit on here, right? What's the composition of the melt?
It's a little more calcic, but it's still super sodic.
It's still sodic, right? It's different than the rock you're starting with. That's the point here, is that the initial partial melt is different than when you start with. If you kept melting it, what would happen? Because you're taking sodium out in the melt, right? What happens to the amount left in the crystals behind? It becomes more calcic rich. And it goes up and up and up and up and up and up and up, and at this point it's completely melted. What is your liquid at that point when it's completely melted? Same thing that you started with. What was the last crystal you had? The very last crystal that hung on. Very calcium rich, right? So this area in here represents solid solution, which means the mineral, plus some liquid. Okay? We'll go through this again next week to look at it as well. The whole point of this is when you start with that peridotite, which is olivine, which is a solid solution. We can look at that. We could put up a olivine phase diagram and look a lot like this. The very first stuff you melt is different than the stuff that's there. Because basalt is not garnet, right? Not garnets in basalt. There's lots of plagioclase, lots of pyroxene, some olivine. See any garnets? No garnets. But when you melt garnet, and we'll show this with the next class, you get a melt that's very different than garnet itself. And that's the whole point, is that the initial melts, we're not melting the whole mantle. We're only melting 5-10% of it at the most. So your melts initially are really different than your starting material. And that's all these phase diagrams are designed to show. We'll go through the same diagram next week, along with some others, and kind of look at how all this melting proceeds. I think next week will be our last week on sort of background, and then we'll erupt the stuff. And watch it come out of the ground and mess up stuff and kill people. All right? So this is a good place to stop. The next section takes a little more time than I have to devote to it today.